Last lecture. So it's 21. Let me get my pen. So it's the last one for the summer. So we're going to talk about exponential functions. So you see this variable x appears in the exponent. That's why it gets a name. Exponential function. Exponential function, right? Because x appears, x is a variable, appears in the exponent. But when x appears in the denominator, we call it rational. Okay, the first question wants us to evaluate. So the function given is 2 raised by x. The base is 2. X is in the exponent. And we want to evaluate when x given as 5. So we just read as f of 5, right? Because x now equals to a specific value 5. So that's 2 raised by 5, right? 5 is the input. So x is the input. The function is defined as raised 2 by the input. So input now is 5. So we raise 2 by 5. And 2 raised by 5 is 2 times 2 times 2 times 2 times 2, 5 times. 2 times 2 is 4. 2 times 2 is 4. 4 times 4, 16. 16 times 2, 32. So this is evaluation. So given the variable value, evaluate the function value. So this is called a function value. F represents a function. So function value at x equals to 5. Now let's see B. B is a function base is 5, based by the variable x. And we want to evaluate when x is -2. So we write as f of -2. Because x is given now as -2. So that's a 5 raised by -2. Remember the negative exponent means this. Like 5 raised by -2 means 1 divided by 5 raised by +2. Or 5 raised by +2, 5 squared is 25. So that's 1 over 25. So this is just evaluation, right? Given the variable a specific value, they evaluate the function value at the given x value. So number 2 is to graphing those two functions. So I have an f function defined as 2 raised by x, g function defined by 2 raised by -x. So let's make a table value. So whenever we graph functions, we can go to table values. So we give x, because x is an independent variable, which means we can assign x any value we want. Usually we give very convenient values. Let's see, we give -2, -1, 0, 1, and 2. Then let's evaluate f of x. So f of x is 2 raised by x. So this one is 2 raised by -2. That's 1 over 2 squared, which is 1 over 4. Right, so we get -2 a quarter as a point. So when x equals -2 here, a function value is positive quarter. So it's a half of a half, half, half. So we get a point somewhere here. At this point is -2 and quarter. Then -1, 2 raised by -1, that's just 1 over 2 raised by 1, which is a half. So -1, we get a half. We get this point. 0, 2 raised by 0, or anything raised by 0, that's 1. So we get 0, 1, the y-intercept, this point. Then 2 raised by 1, just 2. So 1 comma 2, get this point. Then 2 raised by 2, 2 squared, which is 4. Then 2 comma 4, this point. This keeps going. So our graph looks like this. The graph connect those points. So the right-hand side keeps going to the positive infinity, and the left-hand side also keeps going, getting close to x-axis, but it will never cross x-axis. Because 2 raised by any number will never be negative, so it won't go below x-axis. 2 raised by any number will always be positive number, so the graph is above x-axis. So this is the graph of 2 raised by x. Now let's change color to do g. G is 2 raised by negative x. So g of x. So 2 raised by negative 2. So 2 raised by negative 2. Right? Because x itself is negative 2. So negative 2. That becomes positive 2. So 2 raised by 2, this is 4. Then here we have 2 raised by negative 1. That becomes 2 raised by 1, which is 2. Or 2 to the negative 0, or still 2 to the 0, which is 1. 2 to the negative, then the x value is 1. So that's half. 2 raised by negative 2. That's 1 over 2 squared. That's 1 over 4. Right, so get these points. So let's see. So we have negative 2, comma 4, negative 1, comma 2, 0, comma 1, 1, comma half, and 2, comma quarter. Right. So negative 2 and 4. Negative 2 is here. 4 is here. Negative 1, 2. Negative 1 is here. 2 value is here. 0, 1. Overlap the blue color. 1 comma half. This one. 2 comma quarter. Getting closer to x-axis. So the graph goes this way. Yeah, as you can imagine, the left-hand side goes up to positive infinity. The right-hand side goes getting closer and closer to x-axis, but it will never cross x-axis. Because once you cross x-axis, you get all those negative values. But the function 2 raised by any number will never be negative value. So we see these two graphs actually are symmetric with the y-axis, right? So this is 2 raised by x, this is 2 raised by negative x. Well, 2 raised by negative x, we can also think as 2 raised by negative 1, then x, which is a half raised by x. So those are the two graphs. And the blue one, usually we call, because it's growth, right? The blue one, we see the function increases. So we call this one exponential growth. It's a positive relationship between x and the function value. But the red color we call decay. Exponential decay. Decay, why? Exponential decay. So the left application, the exponential growth, we can think about institution, right? We deposit money into the institute. The institute offers us a compound interest. That's the exponential growth model. An exponential decay model we can use for a bioscience, like the bacteria has a certain life, right? So when you raise bacteria, then goes on with time, the bacteria die out. So the dying rate is exponential decay. Okay, lastly, what is the domain and the range of those two functions? We say domain means x value. X goes to the left-hand side of negative, right? Because this is going to keep going, keep going, keep going. And on the right-hand side, right, this keeps going, and we'll take all the positive x values. So the red color is opposite, but the domain are the same. The domain takes all real numbers of x. So domain is all real numbers. So we represent with interval notation, going from negative infinity up to positive infinity. What about range? Range talk about the function value, right? So range is actually 0 up to positive infinity, right? Because it will be greater than, because actually will never reach 0. The function value will never reach 0. So that's why we use open parentheses. We don't use bracket, because 0 will not be there in the range. But it gets as close as to 0 as possible. So those are exponential functions. 2 examples. Let's see, 4, 3, not 4. So 3 is talking about the exponential growth model, the life application for exponential growth function. So usually the institution or the banks offer interest rate for our deposit, right? So let's see question 3. Find the accumulated value of an investment of 77,000 for 5 years at the interest rate of 4%, compounded annually, monthly, compounded continuously. Okay, with this, we have 2 models, which means we have 2 functions, 2 exponential functions. So the first one, let me write on the top. So compound, so the first one is a compound. Yeah. Compound n times. Okay, let's understand the word compounded. What does compounded mean? So when we invest money in the bank, in the institution, right? Let's see 7,000 in this case. That's called principal. Then the bank will calculate interest according to the interest rate. So then they will add the interest to this. When they add interest to this, so next time when they calculate interest, they take this as principal. So your principal keeps changing. So every time they added the interest to your principal, so your principal is increasing. So that means compounded. And that's the word compounded mean. So we have a formula like this. We have a formula. I'll explain the letters. So let me write first. So A equals to P times 1 plus R divided by N raised by N times T. Okay, A means accumulated value. So you can imagine in this case, how much money in the account after 5 years. So that's accumulated. So your balance, your up-to-date balance. P is the principal. In this case, 7,000. principal. And 1 plus R divided by N. R is this annual interest rate. It has to be annual interest rate. Okay. If it's not annual, we have to convert it into annual interest rate. N is how many times being compounded. How many times being compounded means how many times interest being calculated, then added to your principal. If it's compounded annually, N equals to 1. Compounded monthly, we have 12 months in a year. Compounded continuously, we have another formula. So compounded continuously, we have 1 plus 1 over N raised by N. Then in the future, you will learn this. As N gets bigger and bigger, so this we call Euler number. So the formula becomes the accumulated money, the balance equals the principal times E raised by R times T. Okay, what is T? T is how many years your money stay in the account. So in this case, it's 5 years. Okay, what else? And that's it. Now let's see, let's calculate. Let's calculate A1. That means compounded only once annually. So principal is 7,000. 1 plus R interest rate is 4%. Remember 4% is 0.04. Then divided by 1 annually, because N equals to 1. Then raised by 1 times T. T is 5 years. So 1 times 5. So that's 7,000 times 1.04, right? Because inside the parentheses are 1 plus 0.04 divided by 1. This is 1 plus 0.04 becomes 1.04. Then raised by 1 times 5, which is 5. Then we can use calculator or some online, because online usually I use decimals to calculate, but I won't be able to switch to decimals, so I'm going to use my calculator to calculate this. And so how would I press into calculator? I would do 1.04 first. So enter 1.04, then raise by 5. I don't have raised by 5. I'm doing on my phone. So I'm going to multiply 1.045 times. Okay, I get a 1.216. So let me write 1. So when we press into calculator, we calculate 1.04 raised by 5 first. I'm not sure if I made a mistake, but my calculator shows me I have 1.21665. And of course, that decimals afterwards. But this is enough for me because talking about money, we only have to leave 2 decimal points. But I leave more because I have to multiply by 7,000. So now I multiply by 7,000. So I get $8,516.57. Because I get a 0 after 7, I just ignore it. If the number after 7 is bigger than 5 or equal to 5, I would carry on to 7 to make 7 to become 8. So now, so the first one, if compounded annually, the amount of money in the account would be $8,516.57. Right. So that's compounded annually. Or compounded monthly, we just have to change. Let me use my red color. We just have to change this to be 12, right? Because monthly N equals to 12. So then this here is 12 times 5. So then 0.04, let me use my calculator again. 0.04 divided by 12. Then, oops, 0.04 divided by 12. Then plus 1. I have to use, I don't really have a calculator on my hand. But for you to do is this. Let me just rewrite on this side. You have to do 7,000 times 1.0033 raised by 12 times 5, which is 60. Okay, so on your calculator, you have to press 1.0033 raised by 60, then multiply by 7,000. All right. That's also about 8,000 something, but I'm sure it's bigger than this number. It's bigger than this number. So compounded continuously, we have to apply this one. Principal is still 7,000. And E is all your number. So this E number is on any calculator. It's about, so E is like a pi. It's an irrational number. It's about 2.712. So E raised by R is 0.04 times T. T is 5 years. Okay. So I have 7,000 E raised by 4 times 5, 20, but we have 2 decimal places. So E raised by 0.2. All right. And then on your calculator, you do E raised by 0.2. So I'm going to approximate this. So I do 2.7128. Oh, I don't have a raised by actually. Yeah, I'm using my phone. I don't raise by. But this number will be bigger than both of this. Because you compounded continuously means every second you think about it, the interest is being calculated and added to your principal. So it keeps compounding. Okay, keeps compounding. All right, so 3 is the life application for exponential growth model for exponential functions. All right, let's see question 4. So given function, linear function, right? Because x raised by 1, polynomial degree 1, or linear function. And g is polynomial degree 2, or quadratic function. So we're asked to find the composite functions. What does the composite function mean? So we have this f with a little circle of g. So this means, let me write it here, means f takes a g as an input. So you see, usually we have f of x, right? But now the x is g of x. So how do we understand this? Think about it, we have a machine. The machine is f, right? We input something, we input an x. It should come out something, usually come out f of x, right? But inside this machine, we have another machine. So when we put an x in, the x first go to this g machine. So it comes out g of x. So then f takes g as input. So it's like machine inside another machine. Then we just put g of x inside. So what is g of x? Is x squared minus 2. So we put it inside the parentheses. So now this is our input, f of, so don't think about x, those x's are the same. Think about the x is just an empty container. Okay, empty can be anything, can be any expression. So here we just read as f of input, right? So this function is the same. F takes the input, subtract 1 from the input. And g takes the input, square the input, subtract 2 from the input square. So for this case, right, which is the input minus 1. So our input is x squared minus 2, then we minus 1. We simplify this, get x squared minus 3. That's it. That's f composed with g. So this little circle here means exactly f takes g as the input. Now let's say g of x. That means g takes f as input. If you think of the machine, g is the outside machine. G is the outside machine. So when we put in x, it first go to the inside machine, f first. Then comes out f of x. Then when it out of G machine, that's G of f of x. So G takes f as input, or f is x minus 1. How is G defined? G says square the input, subtract 2. So we square the input, subtract 2. Right? Our input is x minus 1. So we square it minus 2. And you can leave like this. You don't have to expand this. Just leave like that. So this is talking about composition functions. Let's see 5. 5 talk about inverse functions. So inverse function, let's see. What is inverse function? So this is f of x equals x minus 1 divided by 2. Its inverse should be, we multiply by 2 first. So we get 2f of x equals to x minus 1. Then we plus 1 on both sides. So we have 2f of x plus 1 equals to x. Then we switch. We call this x f inverse of x. Then we switch f of x as 2x plus 1. So this is the inverse function of this f. So what did we just do? We solve for x. You see, we go through the step to solve for x. Then change the notation. We change x to be inverse function of x. We change f of x to be x. So indeed, you see the inverse of f is 2x plus 1, and g is indeed, g is 2x plus 1. So they are inverse functions. But here, we want to verify this. We want to verify, let's see the machine. Right, machine like this. If we take f of g, in the end, this f of g of x equals x. So it doesn't change. You see, we input x going through G machine, going through F machine, and then we get x back. Same thing here. We input x, go through F machine, go through G machine. In the end, we also get x back. If that's the case, that means those two functions undo each other. They're inverse with each other. Well, let's check. So let's do f of g, right? G is 2x plus 1.
So let's say it breaks it now.
2x plus 1. And we want to verify if this equals to x. So f takes g, right? Then the function defined as input, subtract 1 divided by 2. So our input is 2x plus 1. Input, subtract 1 divided by 2. 1 minus 1, 0. We have 2x divided by 2. 2x divided by 2, indeed, equals x. Yes, verified. Well, let's verify g of f. G takes f. X minus 1 divided by 2. Now, how is g defined? It's just that multiply by 2 with the input. So we multiply by 2 with the input. Then plus 1. Or 2, so we get a 2 times x minus 1 divided by 2 plus 1. Right? This is a 2 over 2, x minus 1 plus 1. 2 over 2 is 1. You have x minus 1 plus 1, minus 1 plus 1, 0. Okay, also verified. So indeed, that means g of x actually is f inverse. So we use f raised by -1 to indicate its inverse. All right. They are inverse with each other. So inverse here means this: f composed with g composed with f equals x. And we call this identity function, right? When we have machine, we input x, doesn't matter what this machine is, then the output also x. It's called nothing changed. You know, this machine doesn't change anything, so we call identity function.
Yeah, I think I looked at some of this earlier on.
Now we're going to so exponential function, its inverse function are called log function, logarithmic function. So logarithmic function. Those are inverse with each other. But now let's get to know these logs. So log. So what does this mean? So if we have, so this equivalently mean 2 raised by 5 equals to 32. So 2 raised by 5 equals 32. So this is the exponent 5, right? So whenever we see log, we can train our brain to think that's the exponent of the base. That's the exponent of the base. And then this here is the value. So you see 2 raised by 5 equals 32. And if we go to B, we see 4 raised by 2 equals 16. So what is log? Log is just basically rewrite the equation of exponential equation, right? In terms of emphasizing on the exponent. So these are equivalent, okay? Those two are equivalent expression. Let's see 7. We want to write exponential equation into log form. So base is still base. So base in the exponential form is base in the log. You know, look at where I read 3. I read the base, you know, at the foot of log. I read it very small. So log base 3 of the value 81 is 4. Right? So 4 equals log base 3 of 81. For this one, I can start with exponent 3 equals to log base 2 of 8. That's it. Even log looks strange, but the idea is very simple. Now let's see 8. We want to evaluate those. So how do we evaluate? And this one log, we can write as log base 10. Now this is 1, 2, 3, 4 zeros. 4 zeros we can write as 10 raised by 4. A log has a property, has many properties. If we have log A base B raised by some C, then we can pull this C up front. Let's see log base AB. So that means this 4 we can pull up from the log base 4, 10 of 10. Well, log base 10 of 10, let's look at this one. Log base 10, value is 10. This has to be 1, right? Because 10 raised by 1 equals to 10. So when the base and the value are the same, it's just equals to 1. Now let's see B. B is obvious, right? B is the base is 5, value is 5, so that equals to 1. Because the 5 raised by 1 equals to 5. Let's see C. C log base 125. Right? So we can do this in 2 ways. So I explain the 2 ways. One way is we can think log base 125, and 5 we can think is cubic root of 125. Because 125 is a 5 cube. 125 equals to 5 cube. Or 5 equals to cubic root of 125. And remember cubic root, we can write it as 125 raised by 1/3. So this one we can write as log base 125. Then value 125 raised by 1/3. Then this 1/3 can be pulled up front. Then we have log base 125. 125. The base and the value are the same, equals to 1. So 1/3 times 1, just 1/3. So C equals 1/3. And D, let's say we don't know this value, right? ln means log base E. E of 1 equals to X. So can I rewrite this one as E raised by X equals to 1? Well, what's the E raised by? Anything equals to 1, that has to be E raised by 0. Right? Anything raised by 0 equals to 1. So ln is log base E. Right? Let's see 9. 9, we have this exponential growth, right? Growth means the base is greater than 1, is 4. And we have this log function. So let's draw the first one. Let's make a table value. Give a couple values of X. Then evaluate f, evaluate g. So let's say this is f, that's g. So let's give negative 2, negative 1, 0, 1, and 2. F is 4 raised by x, so 4 raised by negative 2. That's 1 over raised by 4 squared, 1 over 16. This is 4 raised by negative 1, which is 1/4. 4 raised by 0, which is 1. 4 raised by 1, which is 4. 4 raised by 2, 16. Well, let's graph f. So negative 2, 1 over 16. Negative 2 here, 1 over 16, very small, very close to x-axis. We have negative 1/4. Negative 1/4, also very small, somewhere here. And the 0, 1, 0, 1, somewhere here. Then we have 1, 4, 1, 4. Then we have 2, 16. You see this exponential function increases very fast, very sharp. Right? Very sharp, increases very fast because the base is 4. Base is 4. Every time uses 4 times it, right? Is a quarter is 4 times 1 over 16. 1 is 4 times 1/4. 4 is 1 times 4. 16 is 4 times 4. And the left-hand side keeps going, you know, approaching to 0, approaching to x-axis. Now let's draw G. Let's use red color. So have log, let's evaluate one by one. Oh, we won't be, okay, log won't be able to get a negative value. Not even 0. Log, we need a couple more values. Let's do, so log 1, right? So log base 4 of 1, that's 0, because 4 raised by 0 equals 1. Then log base 4, we better do 4. That equals 1. Right? Log base 4 equals 1. Then log base, okay. So this is a 2. I should make this one here. So log base 4. Log base 4 of 4 that equals 1. And then what do we want x like? So let's draw these points anyway. So get a 1, 0. We get this common point, 1, 0. And then we have 4, 1 of 4, 1. So 1, 0, 4, 1. Yeah, this is 1, 0, right? Little bit high, I should do, a little bit high. Then I have 2, so 1, 0. Oh, I did it wrong. 1, 0 is here. Oh, it's 1, 0. So I have 1, 0, I have this point. Then I have 4, 1, 4, 1, this point. And next one, too big. Maybe just let's do one more. Let's do 2. So log 4 of 2. That's log 4 of square root of 4. That's half, because square root of 4 can be written as 4 raised by half. Okay, so if I get 2, I get a half. So 2 is here, I get a half. Half is somewhere here. So basically my graph, I could do more points. So basically my graph goes this way. The two graphs are symmetric with a line y equals the x line. So this line is called y equals to x. And any inverse functions are symmetric with this y equals to x. Right? So exponential function and logarithm function are inverse functions with each other. So how do we find the domain of log function? Which is this value has to be greater than 0. So this is similar when we're doing radical functions, right? You have radical function like this, which the domain is the radicand cannot be negative or greater than or equal to 0. So for log functions, we see they only take a positive x values as input. So that means this function, this value here has to be positive. So which means this has to be x greater than 3. Right, for this one. And for this one, the domain is x has to be greater than 0. So it basically takes y-axis of line of asymptotes. All right, so that's the domain of log, which means this value has to be positive or greater than 0. It cannot be 0. It has to be greater than 0. Okay, that's it. That's all the 10 questions for the last lecture.